Today we will start with discussing Newton's method. Newton's method is one of the most important methods for solving unconstant optimization problems. So, we will consider a function Rn to R and f would be assumed to be twice continuously differentiable. Now, if that is the case, the question is what is my descent direction? In this case, if the Hessian matrix is positive definite, then T is equal to minus, because it is positive definite, I can take the inverse of the Hessian matrix. This can act as a direction of descent. So, why? Because the question is D a direction of descent? So, consider take is D a direction of descent? So, let us see. So, what? So, there suppose there is a point where grad of f(x) is not equal to 0, and let us see what does this give. This will give us now if A is positive definite, so is A inverse. So, this being positive definite, so this is also PD matrix, positive definite matrix PD for positive definite. So, this would become negative, and hence this is now, this would give you a descent direction. So, this direction is often referred to in the literature as Newton direction. We will come why it is called the Newton direction, but we have few questions to answer before this. Now, the question is as follows: why we at all need Newton's method? Because Newton method needs the function to be twice continuously differentiable, means not only it is differentiable, its second derivative or the Hessian matrix is also continuous as a function of x. But we were doing fine with the steepest descent method, possibly because we had just to bother about the gradient and did not bother about computing a matrix. So, we are increasing the computation cost by bringing in a Hessian matrix. So, what is the problem with steepest descent method? That is the question. So, this fact let us explain on the board what really is the problem with the steepest descent method. So, in the steepest descent method, what you have is that your D is say the negative of grad of f(x)k, where xk is the kth iteration point. Now, what we want to show is the following, that if here I have xk Then suppose my descent direction from here is this is your dk, which is negative of grad f xk. So, if this is my xk plus 1, then the descent direction from there, that is negative of grad f xk plus 1, this would be perpendicular to dk. As a result, the steepest descent method, if it has to move, if this is the actual optima, my x bar, then it will move in this way, in this sort of zigzagging pattern, and this may just delay the progress towards the optimum, and that is the whole issue that lies at the core of the steepest descent method being not used so much in practice, and one has to bring in such methods that we are going to discuss, like the Newton's method here. Now, let us see why this is so. See, one of the ways to find the step length, that is how much you have to move along the direction alpha to obtain a sufficient decrease, is obtained by theoretically by minimizing this function. Now, because I have put alpha strictly bigger than 0, and suppose there is a minima, I have obtained a minima which is alpha k, right, that is what I put as alpha k. Now, suppose I have got the minima as alpha k here, or alpha naught, whatever you want to say, alpha k, that is what I say by the minimum. But here I have looked at only over alpha strictly bigger than 0, and this alpha strictly bigger than 0 is an open set. We have not yet discussed much about constraint and unconstrained optimization, because here what you have is constraint optimization. But I want to tell you something, that if you optimize a function or minimize a function over open set, the necessary optimality condition is nothing but the gradient of f at x is equal to 0, right, because if you really talking about open sets, then we would all observe that, as we will see later in the Karush-Kuntakar condition, that all the constants will become so called inactive constants and their Lagrange multipliers would be 0. So, what is very important to note here is that I can just obtain some alpha k is the solution, because there is xk plus 1. If alpha k is the solution to this problem, then my necessary optimality condition is this. Though I have told you there is a paradigm shift between the between a constant problem and an unconstant problem, but it is important to know that when you have open set, the necessary optimality condition of a constant problem and an unconstant problem is the same. If you are minimizing a function over open set, please note that it is same as minimizing over the whole space. Now, what would I get? From here I would get the following. So, now there is a alpha k strictly bigger than 0 which solves this. So, this happens, this is a necessary condition, and this would give me what? It will give me grad of f of, so my f dash this is nothing but xk alpha k dk into this. You see, what I do is I applied the chain rule. First I took the gradient with respect to this, and then took the derivative of this with respect to alpha, which is nothing but the vector dk. So, we have to write the inner product, because we can't have multiplication, because we have functions from space Rn to R. Now, what is this part? This is nothing but xk plus 1. So, I can write this as grad of f of xk plus 1 into dk. But what is this? By the definition of steepest descent method, this is nothing but the negative of the descent direction, and this would simply imply that this means that these two directions, the consecutive descent directions are perpendicular to one another, and that is why it slows down the whole process. So, our conclusion here is steepest descent method is a very slow process. So, Newton method is one of the faster processes, and so we need faster processes because we just have slow processes here. The steepest descent is a slow process. Now, of course, it is not very difficult to write down the Newton scheme. How do I write the Newton iterative scheme? Okay. So, this question is not difficult enough because you know that you are looking at line search problems where your x of k plus 1 at iterate is x k plus some scale factor alpha k into dk. But then so in the Newton scheme should possibly look like this. This is quite natural because this is minus of this is dk and this is alpha k. So, you are replacing dk with minus of this, but that is that what we all have to the Newton scheme. But the question is first now next natural question is, how do I know that I have to choose dk in such a pattern? How do I know, how do I arrive at the form of the Newton direction itself? Now, here is a very crux issue which lies at the heart of analysis, because it takes something from the Taylor's theorem. You see, if you look at say a function like sin x, now if you look at all x which is very near 0, then sin x can probably be approximated by x, because there is very minute difference between x and sin x here. But as you move away from 0, there is a curvature here and the curve actually moves off from the straight line y equal to x. So, instead of having a straight line to approximate the curve, which is the steepest descent method, we now use a quadratic function to approximate the curve. And if we do so, if we use a quadratic function to approximate the curve, then we would lead to the Newton's method. So, we are not using our exact function or actual function, but we are using some sort of approximation of the function. By instead of approximating it through a linear function, we are approximating it through quadratic function. If you approximate it through linear function, you get steepest descent method. If you approximate it through quadratic function, you will get the Newton's method. So, let us see what sort of thing we intend to do here. So, let x k be a point . such that so xk is not a minimum point. Now, what I require is the following, that so consider the quadratic approximation of the function around x bar xk. So, consider the quadratic approximation of x around xk, which means I will define a function like this, q of x is f of xk. So, xk is fixed, so x is a variable. So, basically I am taking only the Taylor series part. If I want to express the function value of f at x in terms of the Taylor series, this qx is nothing but the Taylor series part without the remainder term, without the error term. This is what I have. Now, suppose I have a point, I now try to minimize this function. So, instead of minimizing the original function, I try to minimize its quadratic approximation around xk. So, what sort of a function is this in terms of x? In terms of x, this is a strongly convex function. We have done a bit possibly about strong convexity. Let us go back and have a look whether we have spoken about strong convexity at all. So, we have not spoken about strong convexity, we have not spoken about strong convexity. So, let us speak about strong convexity. What sort of a function is this? Here we have spoken about strong convexity, right. So, you see we have spoken about strong convexity earlier. So, any quadratic function with a positive definite Hessian is strongly convex and it has a unique minima. So, this is we have assumed that the grad square of f, the Hessian matrix is positive definite. So, this q is a strongly convex quadratic function. Then this will always have a minimum. So, you might ask me why it will have a minimum. Unfortunately, the total detailed explanation of those things are possibly beyond the scope of this course, because this is a foundational course, because that would need a lot of more mathematical analysis and details, which many of the people in the audience, for example, those who are in the engineering stream may not appreciate and may not like to go through it. But it is instructive to know that strongly convex functions would always have a unique minimum and it always would possess a minimizer. Then there exists, so this is always PD, that is assumed. There exists a minimizer x tilde of q over Rn. This would imply that q of x tilde, gradient of q of x, this is 0, the standard necessary condition. So, what would this necessary condition give me? That is the next question. See, this would give me plus grad square f of x k x tilde minus x k is minus of grad f x k. That would lead to the following. This would lead to because of the invertibility. So, x tilde sorry, here I need to put the negative sign. So, this can be written as x tilde is equal to x k minus you will get this one, and then observe the following, that this x tilde can now be written as x k plus 1. So, my Newton iteration so you might question me, what about that alpha, the line search parameter? You just have the d, you have written x k plus d. Here the line search parameter alpha k is equal to 1, we take it alpha k to be 1, a constant 1. So, this is called a pure Newton iteration. And if you take this one that we have written earlier, which comes out naturally, finding some alpha k this is called the damped Newton iteration. What is the geometrical idea behind this? The geometrical idea is possibly of this form. So, suppose you are trying to minimize some sort of paraboloid or some nice looking function of this form. I am just trying to give us some sort of 3-dimensional viewpoint. So, the minimizer is here, actual minimizer, and you are now at some x k here. So, you are trying to have around x k, you are trying to get some sort of course sorry x k is here. So, this is your f x k. So, you are trying to get some sort of another quadratic approximation to this problem, to the function. So, this is your q x, and then you minimize this, which is, so you have come possibly a little bit near to x bar. So, this is the pictorial idea of the Newton method, idea of using quadratic approximation, because if you are approximating by a strongly quadratic problem, you are actually getting a nice result, what we just have. Pictorial idea of using quadratic approximation. Okay. Now, the important question is how fast or how good is the Newton method? My question, how fast or how good is the Newton method? So, in other words, I am asking this particular question. I am asking that what is the rate of convergence of the Newton's method? So, this is an important question, but there is a crux. The Newton method is very fast. In fact, the rate of convergence is quadratic. That is the difference between xk plus 1 with x bar is less than some constant times xk minus x bar whole square. C is a constant, of course. So, this C is a constant. But there is a major crux here. You know, you cannot say, okay, I will start from anywhere. My x0 should be at any point in Rn, and I will very rapidly come to the solution. The Newton method would be the greatest thing of all, at least for strongly convex functions, maybe which are not quadratic. You have these method will just work like magic. But it is not so always. It's the problem with Newton method is that quadratic convergence is assured if I start very near the actual solution, but how do I know what is the actual solution? So, the drawbacks are as follows. Quadratic convergence assured only if we start very near the solution, very near the actual solution. Now, this is a drawback. Another major drawback is that what would happen if my problem is such that at every point I do not have a positive definiteness of the Hessian, which means that if I do not have positive definiteness of the Hessian, I have to stop it and go back to the slow steepest descent method. Isn't there something which can help me? So, the question is, if grad square fx is not positive, that is, the problem is not strongly convex, is not positive definite everywhere, then what? So, these drawbacks has led to what we will study later as to quasi-Newton methods, which is one of the major methods for solving unconstant optimization problems, where there is a very clever way to imitate the Newton method, but handle situations where this is not true. Now, let us write down a important result associated with the Newton scheme is its convergence. So, this is a convergence theorem for the pure Newton method. Now, let us write down the result, the theorem. So, let f be a twice continuously differentiable function. Now, we have to put assumptions on the Hessian etc. to get the convergence, but there are various authors giving various results. We are writing one given by in the following book, Mathematical Methods of Optimization by Lars Christian Boyres. Please have a note of this. Mathematical, this is an Indian edition, so you can also use it. But there are many other approaches. Let grad square fx be PD, positive definite throughout Rn. Then when x is sufficiently close to A, sufficiently close to x bar, the actual solution when x is sufficiently close to x bar, the actual solution, let the matrix norm. So, how do you take the norm of a matrix? Now, these are all symmetric matrices. You have learned how to take the norm of a matrix, but here possibly they are meaning the operator norm, the norm of a matrix. So, those who are little uncomfortable, please do not bother much about this terminologies at this moment. And so, you are making some too strong assumptions. So, if the initial x1 in the initial point x naught or x1 initial point x naught be close enough to x bar, then xk tends to x bar with a quadratic convergence rate. Now, where xk are the pure Newton iterations, are the pure Newton iteration values. There is no the alpha k is 1. So, this is a very now you might ask me what about this, too much of conditions. So, in the class I will try to give you a simpler condition, certainly a different condition, but let us go and try to do the proof. Now these A and B are constants. So this A and B here, A and B are constants. Of course they are positive constants because or non-negative constants, because here these are norms, right, and the Hessian matrix is not a 0 matrix or something like that, because 0 matrices cannot be invertible, right, because they are not PD matrices, because all their eigenvalues would become 0. Okay. Now, how do you go about proving this fact? Now, from the Newton scheme, we will use now the Newton scheme. So, x k plus 1 minus x bar. So, we have to find the quadratic convergence is x k minus, so I am writing x k plus 1 as x k minus the Hessian matrix inverse into grad of f x k. Now, remember grad of f x bar is equal to 0, because that is the solution. So, I can write this as so this would imply norm of x k plus 1 minus x k. Okay. So, I can write this thing as norm of grad square f x k inverse into grad square f x k, this whole thing into x k minus x bar minus grad square f x k inverse into grad f x k minus grad f x bar. We are taking the norm of this whole. Now, this would turn out to be like this, that I can take all these things out common. So, this would be by Cauchy-Schwarz inequality, basically the standard the norm of a vector is norm of some a, or norm of a x is less than equal to norm a into norm x, that is the definition of the operator norm. So, those who do not know about the operator norm, please do not get into a fix. Just I would like to go in and tell you that the norm of a matrix, the one which has been used here, the operator norm, the norm of a matrix A, symmetric matrix here in fact, the norm of a matrix A is given as supremum of norm of the vector Ax, n cross n matrix, by norm of x, when norm of x is not equal to 0. So, that is called the operator norm of the matrix. So, here we are using the operator norm, and from here by definition you will see that this is a supremum of this. So, each of these is less than equal to norm of A. So, norm of Ax is norm of A into norm of x. So, using that same thing we can write now f x k inverse norm into norm of f x bar minus f x k minus grad square f x k x bar minus x k, and this is less than a. So, a and this whole thing by your, because x is where now for k sufficiently large. So, this can be written as by definition here x minus x bar or x k minus x bar whole square. So, a b is my constant c. Now, this is what is called the quadratic rate of convergence, because c is the, here is my, this is my constant c. So, I have got the form of quadratic convergence. What is remaining, which I want to give you as homework, show that x k actually goes and hits x bar. From this expression, find under what condition x k would actually go and hit x bar. So, I tell you the condition is that if I have a b into norm x naught, which is the starting point, x naught minus x bar, if this is strictly less than 1, then I will have a convergence. So, if so, basically then what I require is that so if x naught is within such a distance from actual solution, then x k, the things that you have, the pure Newton iteration points will go and hit x bar. And so, this gives us a nice way to sum up the quadratic convergence as well as the convergence of the iteration points. So, this is a brief study of the Newton method, and then we will go into modified Newton method in the next class, maybe telling you a bit slightly more and giving you some more examples, and then we will study a very important class of method called the conjugate direction method, which is very important and applied in many places. So, we will do that and we will study conjugate direction method with in quite a big detail, and then give you a brief idea about trust region method before moving to study the theory of constant optimization. Thank you very much for today.